that is d by t is less than 20, then we call it as a thick cylinder. Okay, so we have also observed that in thick cylinders we'll be considering radial stress, hoop stress, and longitudinal stress. There will be three types of stresses that will be acting in a thick cylinder. Those are longitudinal stress, hoop stress, and radial stress. We have also discussed in the previous class that the longitudinal stress across the thickness. See, if you see this is the thickness, right? This is all the thickness. Across the thickness, the longitudinal stress will remain constant, whereas the circumferential stress and the radial stress will vary across the thickness. See here, students, as this is a thick cylinder, there will be more amount of thickness. All right, thickness will be greater. So if the fluid gives some internal pressure at this part, see here, the fluid is giving internal pressure at this part, right? So if it gives internal pressure at this part, as this pressure transports to the extreme, it will decrease. All right. So it has to reach to the extreme portion, and meanwhile it will decrease. All right. But the material offers some stress to withstand this internal pressure. That is the property of the material. All right. It offers some resistance to withstand the pressure that is applied. So that will be applied like this, and here it will be more, and meanwhile it will go down like this. Okay, now our problem is to find out what is the value, like magnitude of this radial stress and how it varies along the thickness, and magnitude of circumferential stress and how it varies along the thickness. So for that purpose we have Lahm's theory. So Lahm's theory, yesterday we have made some assumptions for doing this theory. So the assumptions are material is homogeneous and isotropic, plane sections remain plane, and sigma L is constant throughout the thickness. Across the thickness, sigma L is constant. These are the assumptions that we have made. Now let us consider a cylinder, students. Okay, let us consider a cylinder with internal radius. Okay, this is internal radius Ri, and external radius R0. Let us consider a cylinder like this. Let me take this as R0. Is it clear, students? So we have considered a cylinder with internal radius Ri and external radius R0, and there is a pressure of P is acting inside. This is internal pressure, and let us assume some P0 of pressure is acting externally. Okay, if this is in atmosphere, there is no problem, but if it is in somewhere like a submarine or a pipe which is inside the earth, there will be pressure acting from the outside as well. Okay, so P be the internal pressure of the fluid inside, and P0 be the outside pressure or the external pressure that is being applied on the pipe or cylinder. Okay, students, so we have to understand this figure first, and then only we can easily do for the theory. Okay, we can easily solve the theorem if you understand this. Now in this thick cylinder, across the thickness, this is all thickness, right? So R0 minus Ri will be thickness. So thickness is nothing but R0 minus Ri. So across the thickness, let us consider a small strip which is of diameter dr, which is of thickness dr. Okay, so let us consider a small strip. This is all the small strip that we have considered, and let me take the thickness of this small strip as dr. Okay, so and the internal pressure will be P as usual, and the external pressure, I am considering it to be P plus delta P. Okay, So this P naught has transformed to P plus delta P as I'm considering a section, as I'm considering a ring at somewhere from the extreme radius. Now, if you consider this is the sectional view, students, and if you see the side view of the considered ring portion, that will be like this. Okay, that will be like this. I hope you are able to see the figure clearly. The length is L and internal pressure is P, external pressure is P plus delta P, and the thickness is dr. Okay, and I'm considering it to be at a distance of r from the center. Okay, r from the center. Internal radius is ri, external radius is r naught, and I'm considering this particular ring at a distance of r from the center. Okay, now let us get into this theorem, students. So consider a semicircular ring element with internal radius r. So we have considered that. So let me just assume only this semicircular ring portion. Okay, so don't bother about the bottom ones. I'm just considering this top portion. Okay, top portion. Now let sigma r be the internal radial pressure and sigma r plus d sigma r be the external radial pressure. That we have seen, students. We are considering it as PR and P plus delta PR. So for this, if you make it as a stress, okay, because of this application of pressure, there will be stress, right? And that stress I'm taking it as sigma r. Okay, and this stress be P plus P. Sorry, sigma r plus d and this as sigma r plus d sigma r, very small portion. So here P plus delta P, here sigma r plus delta sigma r. That is what I have considered. Okay, now this is the external radial stress and this is the internal radial stress. Radial stress. You may get this doubt, right, students? So the pressure is acting in this direction, the stress is acting in this direction. You have to consider this as this direction and this as this direction. Okay, I have just made it because these two are in opposite direction, so I'm just making it the same. Now if you write the net bursting force of this cylinder, okay, let us write for bursting. Students, it is okay, right, up to now?
Yes, sir.
Okay. So let us write for bursting force, students. Bursting force in the sense, because of the application of the fluid pressure, okay, because of the application of the fluid pressure, let us assume that this pipe will burst out. Okay, let us assume that this pipe will burst out. So what will be the bursting force? So what will be the bursting force in the sense, internally this is having a pressure of P and externally this is having a pressure of P plus delta P. Okay, this pressure will make the pipe burst and this pressure will make the pipe to remain, right? So these two are opposite pressures, opposite radial pressures, and this PR tries to burst the pipe and this P plus delta P will try to resist the pipe. So the net bursting force will be this one minus this one. Okay, so I'm writing it in terms of force. So here I have stresses, right? Sigma r is the stress multiplied by area. So area on which it is acting is 2 into r into L. Okay, so 2 into r into L, so 2RL. Now minus the resisting one is sigma r plus d sigma r into the area is 2 into r plus dr into L. I hope you got this, students. Did you get this, students? So if you see the extreme right figure, observe the extreme right figure, students. Observe the extreme right figure. I have made this figure. The projection of this figure is also been projected downside as rectangle. So the projection of this cylinder will be seen as a rectangle like this. So if you see this rectangle, the pressure P is applying over this shaded portion area, right? Isn't it? Is it clear, students?
Yes, sir.
So P is applied on this projected area, the shaded portion. So I'm just writing it in terms of force. So force is nothing but stress into area. Stress is sigma r that is acting, and the projected area is 2r. 2r is the side of this rectangle. See here, 2r, and other side of the rectangle is L. 2r into L will become the area of the rectangle. Isn't it, students? So this is stress multiplied by area. I am getting force. So this force, internal force minus external force will give us net bursting force. So observe the second one, students, the external one. So sigma r plus d sigma r is the stress that is acting over the area of, see here, we have another two strips here. Okay, two strips of this thickness, right? If you see the rectangle here carefully, beyond the shaded portion, there is small strips of rectangle, white color small strips of rectangle. Isn't it, students? Are you able to see this?
Yes, sir.
So what is the area of that? 2r plus 2dr. So there will be, this is dr and this is dr and this is 2r. 2r plus 2dr. So that is what I have written. I have just taken 2 as common, r plus dr is written here, multiplied by L. L is the side of the rectangle. So this entire rectangle. So for external force, we are considering the entire rectangle, and for internal force, we are considering the shaded portion, orange color shaded portion here. I hope you got this, students. This is the net bursting force. Okay. So once you get into this, it will be very, very easy. Now let us write for hoop stress. Sigma H is hoop stress. So this net bursting force will be resisted by the hoop stress developed in the cylinder. Hoop stress. What is hoop stress, students? We have seen in the while doing this thin cylinders. The hoop stress will be acting like this. Alright. So this hoop stress upon these strips, it will help us not to burst the pipe. So if you see the other end will be like this. Okay, other end there will be in this direction. So this hoop stress will try to restrict the bursten. Okay, this burst. So hoop stress will be acting in this direction, right? So this internal pressure and external pressure will make the pipe burst. So that net bursting force is resisted by the hoop stress of the material. Is it clear, students? So this can be equated to, this bursting force can be equated to hoop stress. So what is hoop stress, students? Let us write for sigma H. So sigma H or the resisting force. Let me take this resisting force. Resisting force. Bursting force is equal to resisting force to make it in equilibrium. So resisting force in the sense resisting stress is sigma H, right? So sigma H will be acting in this portion and there will be strips like this. Alright. So we need area of these strips, right? Area of these strips will be 2 into dr into L. So dr into L is the area of this rectangle. This is dr, right, students, and this is L. So dr multiplied by L is the area of this strip, and dr multiplied by L is area of this strip. That is why I have written 2 here. Is it clear? Now we can equate this bursting force is equals to resisting force. Students, please concentrate, and if you have any doubts, please let me know. Bursting force can be equated to resisting force as the body is in equilibrium. Students, is everything okay? Shall we move forward?
Yes, sir.
So if you equate this, bursting force is equals to resisting force L minus sigma R plus D into sigma R multiplied by 2 into R plus dr into L is equals to sigma H into 2 dr L. So now I have equated and I would like to take out 2L as common. If I take 2L as common, this becomes sigma R into R, okay, minus, so this will become sigma R plus D sigma into, I have taken 2L as common, right, and this becomes R plus dr minus, sorry, is equals to sigma H into 2L put me out in, let us write this, okay, sigma H into dr into 2L. So this 2L will get cancelled, and again I would like to take sigma R into R as okay. So this implies this is sigma R into R minus, if you try to multiply the students, what will we get? If you try to multiply these two terms, this is sigma R into R plus sigma R into dr plus d sigma R into R plus d sigma R into dr, okay, is equal to sigma H into dr. So here if you open this bracket, this one and this one will get cancelled, and now this can be taken as here another thing students, this is very small, so this can be neglected. So this is d sigma R and dr, both are very small things, so this can be neglected. So we'll get like this students. Sigma H, I'll make all these terms to the other side and equate it to 0. Sigma H into dr minus untadi plus పోతుంది అవతలకి పోతే, so plus sigma R into dr plus d sigma R into R is equal to 0. Now divide with dr on both sides students. So divide with dr on both sides, okay, dividing with dr on both sides. All of you please concentrate and follow carefully. Dividing with dr on both sides. So if we divide with dr on both sides, what will we get students? Sigma H plus sigma R, dr will be going right, plus R into d sigma R by dr is equal to 0. Is it clear? Now let me take this as equation number 1 students, okay. Now considering longitudinal strains, considering longitudinal strains, see students, we have already discussed this. So in Hooke's law, wait for a while students, just wait for a while, and where is it? Yeah. All right. So considering longitudinal stress. So you see students, we have already seen this, that in Hooke's law, if the stresses are acting in 3D, 3 dimensions, so like this, like this and like this, what we can do is sigma L. So epsilon L will be acting in this direction, whereas the both radial stresses, so radial stress and hoop stress will be acting in opposite direction. So 1 by E, this we have seen students, sigma L minus mu into sigma H, this is hoop stress, plus mu into sigma R. So why I have written this sigma R is because this plus is because plus ఎందుకు రాసినారు, మైనస్ కదా రాయాల్సింది మనం యాక్చువల్గా, మైనస్ కదా రాయాల్సింది, గుర్తుందా? ఇది ఈ ఫార్ములా రాసింటాం, ఎప్సిలాన్ హెచ్ ఈజ్ ఈక్వల్స్ టు 1 by E ఇంటూ sigma x minus mu into sigma y minus mu into sigma z. This is based on the Hooke's law. But why I have taken it as positive is taken positive because, all of you make a note of this students, because the compressive nature of the radial stress, because of the compressive nature. So if you see here, all the directions are like this, but the radial stress acts in this direction. We have also observed this here, because of the application of the pressure, the radial stress acts in this direction, so the resistance will be in this direction. So this is compressive nature of radial stresses. Okay, so I have taken it as positive. Is it clear? So this epsilon L longitudinal strain can be written as 1 by E into sigma L minus mu common, if you take mu as common, sigma H minus sigma R. Okay, is it okay students? This is sigma L, right? So we have already seen and we have already have it in our assumption that this sigma L is constant, right? And here strain will also be constant, change in length by original length. So this will also be a constant. As sigma is constant, epsilon will also be constant, and E is definitely constant for a particular material. Mild steel, it will be constant. If you consider copper, it will be constant. So Young's modulus will be constant for material considered. Okay, so if all these terms are constant, this is also a constant, right? So if you make this subject sigma H is equal sigma H minus sigma R, then this will also become a constant, right? So sigma H minus sigma R, if you make this subject, all constants will move to the other side. So this is also a constant. So constant in the sense, let me assume sigma H minus sigma R as 2a. Okay, so as a constant, I'm just assuming sigma H minus sigma R as 2a. Let us assume, students, any doubts here? Sigma R as 2a. Okay, so we know under sigma H minus sigma R is equals to all these things subjected outside. So substitute this equation 1. This implies sigma H will be sigma R plus 2a. So this is equation number 2. Substitute in equation 1. Substitute 2 in equation number 1. We get, so what is equation 1, students? So equation 1 is sigma H plus sigma R plus R into d sigma R by dr is equal to 0. So in the place of sigma H, you just substitute sigma R plus 2a. So if you substitute that, what we'll get is this implies sigma r plus 2a plus sigma r plus r into d sigma r by dr is equal to 0. Isn't it? So sigma r becomes 2 sigma r plus 2a is equal to uh, minus r into d sigma r by dr. Is it okay? So let me just take this to the opposite sides. So this can be rewritten as, students, d sigma r, okay, this d sigma r by, so this part 2 into sigma r plus a, okay, cross multiplying అనుకోండి, cross multiplying is equals to what we get is minus dr by r, isn't it? So this dr by r is transferred to that side, so dr by r is come, and this part I have taken it like this. So I have just rewritten the equation. So d sigma r by 2 into this part has become like this, and I'll also make this 2 to go that side. So if it goes like that, d sigma r by sigma r plus a is equals to minus 2 into dr by r. So now let us integrate this above equation. Let us integrate this above equation. Integrating above equation. So if you integrate this, what happens, students? Let me write it. Integral of 1 by sigma r plus a into d sigma r is equals to integral of minus 2 into 1 by r into dr. So if you integrate this, what happens? So 1 by a, integral over 1 by a is logarithm of a plus a. So this d sigma r will go, is equals to minus 2 into ln of r. So this is natural logarithmic, students. Ln is plus c, integral constant. Okay, let us consider assume integration constant c is equals to ln of b. Let us assume this c as ln of b for b is constant. So you have to remember this, students. This is just for our analysis purpose. I am assuming c as ln of b, and similarly in the starting I have assumed sigma h minus sigma r is equals to 2a. These two assumptions you should remember. That is purely for our assumption and analysis purpose. So this becomes ln into sigma r plus a is equals to ln into minus 2 is there, 2 log r will become ln into r to the power of minus 2 plus ln into b, okay, plus log b. So log a plus log b will become log a plus log b. So I wanted to cancel this logarithm, so this becomes sigma r plus a is equals to log a plus log b is log a by b by ab, log ab. So log ab in the sense b into r to the power of minus 2. So I just write this as b by r square. Okay, so b by r square. Is it clear, students? So this is equals to log b into r to the power of minus 2. So b into r to the power of minus 2. R to the power of minus 2 is nothing but 1 by r square. So I have written it that. Now this implies sigma r is equals to b by r square plus b by r square minus a. Okay, so we have calculated, we have seen sigma r in terms of a and b, where a and b are constants which can be found or determined by using boundary conditions. So let us substitute equation 3 in equation 2 to get sigma h. So we have this, right, students? Sigma h minus sigma r is equal to 2a. Okay, this implies sigma h is equals to b by r square minus a plus 2a. Okay. So here what happens is sigma h will become b by r square plus a. So plus 2a minus a. So these two are the equations for hoop stress and radial stress. Is it clear, students? This is the derivation for hoop stress and radial stress. So where a and b are the arbitrary constants. See here, a and b are arbitrary constants which can be found by applying boundary conditions. Okay, so a and b are arbitrary constants which can be found by applying boundary conditions. So what are the boundary conditions, students? Boundary conditions are nothing but at r is equals to ri. Okay, we have sigma r is equals to pi. Similarly, r is equals to r naught, we have sigma r is equal to p naught. Is it clear, students? I hope you got this boundary conditions also. See, I just wanted to make it sure that you understood this boundary condition. See here, students, we have a cylinder like this, right? Okay, we have a cylinder like this. There is an internal pressure, and this is nothing but Ri, right? So Ri, at Ri we have internal pressure of Pi. Similarly, at Ri the stress will be Pi, so equated. So this stress can be equated to this. Similarly, at R is equal to R naught, the stress will be equal to the external pressure P naught. So these are the boundary conditions. Based on these boundary conditions, we can find A value and B value. So sigma r radial stress and sigma h hoop stress are the dependents on this radius. Okay, what is r, students? R is nothing but it is not the radius of the cylinder. It is the radius where we have considered the strip. Okay, so if we have considered a strip here, see, if you have considered strip here, this is R. Is it clear, students? So at wherever portion you want, you can find this sigma r and sigma h based on these two formulas. And you have to find out A and B values by using these boundary conditions. Is it clear, students? I hope you got what my point is. So here this R is nothing but variation across the thickness. So at this point, wherever you consider that point, that length from the center, we take it as R. Okay. Any doubts here, students? Students, please respond. Students, please respond. Is it okay?
Yes, sir.
So we'll try to solve 2 to 3 problems on fixed cylinders, and then we'll move into compound cylinders. So we have another concept called compound cylinders that also have to be discussed, and then we have to go to columns. So it's a long process, students. Don't worry, we'll finish off. So we have 2 problems on fixed cylinders, and then we'll move into compound thick cylinders. The compound thick cylinders will be just one class. Okay. All right. Okay. See, students, you should be aware of all these things. Let me stop recording, and then. So if you have no doubts, students, you can leave and join